Ever get the feeling that the simplest things can be the most powerful?
Hmm.
Today we're diving deep into a concept that proves just that. Smooth numbers.
Now, before you picture us, ranking our favorite numerical desserts or something,
Right.
let me assure you we're talking about some seriously powerful math here.
We're talking about the quiet heroes behind internet security, code breaking, and maybe even cracking some of the biggest unsolved problems in math.
Yeah.
And our guide through this fascinating world, Andrew Granville, a true heavyweight in number theory.
Definitely.
We're looking at excerpts from his paper, Smooth Numbers,
Yeah.
Computational Number Theory and Beyond.
And trust me, when Granville says beyond, he means beyond.
Okay.
But before we get ahead of ourselves, let's start with the basics. What exactly makes a number smooth in the mathematical sense?
Imagine a pebble worn smooth by the ocean.
Right.
No jagged edges, just a pleasingly smooth surface. In the world of numbers, those edges are prime numbers. Those numbers only divisible by 1 in themselves.
Right, like 2, 3, 5, 7, the building blocks of all other whole numbers.
Exactly. So a smooth number is like that perfectly rounded pebble. It factors out neatly into small primes, nothing too big or jagged.
Yeah.
The bigger the prime factors a number has, the less smooth it is.
So for instance, 12 is smoother than 24. Even though 24 isn't that large of a number, it has a prime factor of 2 that repeats itself 3 times, whereas 12 only uses 2 and 3 once each.
You've got it. You're already thinking like a number theorist.
Right.
But here's where it gets really interesting. It turns out we can actually predict, with surprising accuracy, how many of these smooth numbers are hiding amongst all the other numbers.
It's remarkable, isn't it? It seems so counterintuitive.
It really does.
It's like knowing the odds of pulling a heart from a deck of cards, but for mathematical smoothness instead.
Right.
This is where the Dickman-De Bruijn function comes in.
Now, that sounds intimidating, but stick with us. Think of it like this. Imagine a graph that visually represents the likelihood of a number being smooth. That's essentially what the Dickman-De Bruijn function does. It lets us estimate this smoothness probability. And that's incredibly useful in a surprising number of ways.
And here's where things take an even more fascinating turn.
Okay.
Smoothness isn't just some random occurrence. It pops up in very specific sequences of numbers and even in far more complex mathematical structures.
You're telling me even polynomials, those strings of x's and exponents, can have a degree of smoothness?
Yeah.
That's wild.
Yeah, it's pretty wild.
Granville calls this idea the universality of Dickman's density function. The idea that this concept of smoothness and our ability to predict it extends far beyond what we might initially assume.
And what's even more intriguing is that this is still a conjecture.
Okay.
Meaning it's a mathematical hypothesis, not a proven fact.
Right.
Mathematicians are still debating its validity, which just adds another layer of mystery to this whole thing.
Okay, so smooth numbers have this unexpected predictability. They're popping up in all sorts of places. But why should the average person care?
Right.
What are they actually good for?
This is where things go from fascinating to downright mind-blowing.
Okay.
Smooth numbers are like the secret ingredient in a recipe for some incredibly powerful algorithms.
Algorithms. So we're talking real-world applications here, computer science stuff.
Absolutely.
Okay.
Take cryptography, for example, the art of secure communication.
Right.
It relies heavily on the fact that finding smooth numbers in specific contexts can be incredibly difficult for computers.
So it's like trying to pick a lock, but instead of tumblers and pins, it's these smooth numbers creating a mathematical barrier.
A perfect analogy. And just like a strong lock protects your valuables, this property of smooth numbers helps protect our data and communications online.
Right.
Many encryption schemes use mathematical problems that are easy to check if you have the key, often a smooth number, but almost impossible to solve if you don't.
So smooth numbers are essentially both the lock and the key to picking that lock in the world of cryptography.
Exactly.
That's pretty mind-bending.
It is. And this idea of exploiting the difficulty of finding smooth numbers pops up in another critical area: factoring large numbers.
Okay.
You see, to crack many encryption schemes, you need to be able to quickly break down a large number into its prime factors.
That's where things like the quadratic sieve come in, right?
Yes.
I remember seeing that term in the paper.
Exactly. The quadratic sieve and its more complex cousin, the number field sieve, are algorithms specifically designed to factor large numbers.
Okay.
And you guessed it, they rely on finding smooth numbers to do the heavy lifting.
Wow. So we have these smooth numbers playing a crucial role in both creating and potentially breaking codes. But how does all of this tie back to those big unsolved problems you mentioned earlier?
This is where the rabbit hole gets really deep. Remember us talking about how we can estimate the likelihood of a number being smooth?
Yeah.
Well, some of the best tools we have for doing that only work if the famous Riemann hypothesis is true.
The Riemann hypothesis, that's the one about how prime numbers are distributed, right?
You got it. It predicts a kind of hidden order in the seemingly random way prime numbers appear.
Right.
And here's the kicker. If someone could prove the Riemann hypothesis, our understanding of smooth numbers and their applications in cryptography and factoring would take a quantum leap forward.
So we have these smooth numbers,
Mhm.
seemingly simple but secretly powerful, potentially holding the key to unlocking one of the biggest mysteries in mathematics. It's incredible how interconnected everything is.
It is. And if that wasn't enough to pique your curiosity, there's a whole world of even weirder, more specific, smooth number problems that mathematicians are grappling with.
Okay, you've got me hooked. What kind of weird are we talking about here?
Well, there's something called the smoothness and short intervals problem.
Okay.
Picture this. You pick any number you want, no matter how large. The question is, can we always find a smooth number within a short distance of that number?
So it's like searching for a perfectly smooth pebble on a beach full of jagged rocks, but we're trying to guarantee we can find one within a specific area.
Exactly. Sounds simple, right?
Yeah.
But proving it mathematically is incredibly challenging. It's like proving that no matter where you stand in the universe, you can always find a smooth pebble within arm's reach.
That's a mind-boggling thought. But you mentioned another problem, Vinogradov's conjecture. How does that one fit into all of this?
Vinogradov's conjecture is like the flip side of the same coin. It's about finding numbers that don't behave like smooth numbers in certain situations. It's looking for those rare, rough around the edges numbers that buck the trend.
Interesting. So we're searching for the rebels of the number world now.
In a way, but here's where it gets really interesting. Granville suggests a potential link between these two seemingly disparate problems. If we could somehow solve this smoothness in short intervals problem, we might be able to crack Vinogradov's conjecture as well.
Wow. So we have these two mathematical puzzles, seemingly worlds apart, potentially connected by this underlying concept of smooth numbers. It really highlights how interconnected seemingly unrelated areas of mathematics can be.
It does. And while we're on the topic of connections and surprises, I have to share a couple of fun facts about smooth numbers that Granville sprinkled throughout his paper.
Okay.
Did you know there are infinitely many pairs of smooth numbers right next to each other, like numerical twins?
Smooth twins. That's adorable. It's fascinating how these seemingly simple mathematical concepts can lead to such elegant and unexpected results.
It is. And there's another one that sounds simple but has puzzled mathematicians for years. The smooth Goldbach conjecture. It proposes that every number can be written as the sum of two smooth numbers.
So it's like taking those smooth pebbles we talked about and seeing if you can always find two that add up to any number you can think of.
A perfect analogy. And while it hasn't been definitively proven for every single number, mathematicians have gotten remarkably close, which is impressive considering how deceptively simple the conjecture sounds.
It's incredible, isn't it? This whole deep dive has really been an eye-opener. We started with what seems like a simple concept, smooth numbers, and ended up in a world of cryptography, unsolved problems, and potential mathematical breakthroughs.
It just goes to show that even in the seemingly abstract world of number theory, there's often a hidden depth and complexity that can have a real impact on our understanding of the universe and our place in it.
Absolutely. So for our listeners who might be feeling a little overwhelmed right now, what's the key takeaway you want them to remember about smooth numbers?
I think the most important thing to remember is that smooth numbers, despite their deceptively simple name, are a fundamental concept that pops up in some really unexpected places. Whether we're talking about securing our data or trying to solve some of the biggest mysteries in mathematics, these smooth operators are quietly playing a crucial role.
It's like they're the unsung heroes of the number world.
Precisely.
Yeah.
So the next time you come across a hard problem, ask yourself, could smooth numbers play a role here? You might be surprised by the answer.
A fantastic point to end on. A huge thank you to our expert for taking us on this incredible journey through the fascinating world of smooth numbers.
My pleasure. It's always a delight to talk about the beauty and wonder of mathematics.
And to our listeners, we hope this deep dive has inspired you to look at the world around you with a renewed sense of curiosity. You never know where a little bit of exploration might lead you. Until next time, happy learning.